these are models of orbital mechanics. Right now this, and I don't know if you can see that on the screen here, but there's a little dot there. Do you see the little dot moving around? You see that guy? He's going around like that. Okay, and there's two ways that we can think about orbital mechanics for this. Okay, the first way is, and I call this a Newtonian way. I was like, that's not a real pen. Okay. Okay, a Newtonian way. With a Newtonian way, basically, what we do is we think of orbit as an equilibrium between two forces. And I'm going to have to use the F word here. Okay, so I hope you guys are okay with that. You guys okay with that? Okay. There's two principles here, right? And the first is that really basically we've got the force of gravity, which is pulling this thing to the middle. She's not here. She's not in the class anymore. Anyway, there's a force of gravity pulling it in, right? And if you're in that frame of reference, there's also, because you're moving, by the way, the centrifugal force flinging you out. And if you're in a perfect orbit, okay, then those things are balanced and they stay balanced and you go in a nice little circle, okay? So gravity is pulling you in, centrifugal force is flinging you out, and orbit is the equilibrium between those. Do you think about it that way? Does anybody think about it that way? Have you thought about it that way? That's one way to think about it. Yes? Okay. Now, here's a funny thing. Okay? If I am spinning, and all kids in Twin that have grown up playing at IBI Park, okay, notice, can you scoot like that way just a little bit? Snuggle up to him there. Here we go. Okay. There we go. Everybody knows this phenomenon, but if you, for some chance, did not go to IBI Park and make yourself violently ill on one of those things, right? Okay, I'm spinning. If I pull my arms in, I speed up, and if I put them out, I slow down. Okay, this is called conservation of angular momentum, and when we get to momentum, maybe then we can go and talk about why that is. But basically, the way it works is that the amount of sort of spinning momentum, which is how hard I am to spin, times how fast I'm spinning, right, is the same. So if I pull my arms in, I'm easier to spin, so I have to spin faster to have the same momentum. If I put my arms out, I'm harder to spin, so therefore I spin slower because there's the same amount of that product, okay? So with this thing, let's imagine with this, and I'm going to do this on this, is I'm going to slow myself down. The R key slows me down. R is for retro, okay? So I'm going to hit this 5 times, a magic number of times, right? And notice that I then fall to a lower orbit. Yes? Okay. Now here's the problem that we have, is that every kid can solve, and they get that velocity is the square root of gm over r. Okay? And so kids look at this thing, and I always ask this question. This was a question, and it will be on the test. Okay? If I'm in a particular stable orbit, and I fire the rockets so as to slow myself down, what will happen to the radius of my orbit? And kids got it wrong. Like for years and years, kids would get it wrong, and I couldn't understand why they got it wrong. Well, here's why they got it wrong. Look at this. What does this say? This says that if you're going slow, that your radius is, was it small or big? Big. Slow velocities, orbital velocities, correspond with big radiuses, right? And so what they said was if you slowed yourself down, you'd move out away from the planet to a larger radius, okay? Well, they're different things. Those are two different questions, right? One question would be, where are the fast orbits? Where are the slow orbits, right? The other question is, what happens to you if you're in a particular orbit and you slow down? Well, here's what happens, right? If I slow down in this point, let's use our model, okay? Well, if I slow down, gravity stays the same, but what becomes less? Centrifugal becomes less, and so doesn't the planet pull me in? Yes, so there it is. Let's watch. It pulls me in. When I get pulled in, what do? I speed up. When I speed up, right? So, okay, so I go to a lower orbit. When I speed up, well, when I speed up, what becomes stronger now? Centrifugal, so I get flung out, right? Like that, right? Okay, so an elliptical orbit then is this oscillation between being pulled in because gravity is stronger and then being flung out because centrifugal force is stronger. That's kind of a cool way to think about it, isn't it? Yeah? Okay. Now, what if I speed up? What if I suddenly speed up? What's stronger then? Yeah, let's start over again. I'm going to hit enter, and I'm going to go O, and I'm there. O is cheating for putting yourself in a perfect circular orbit, right? What if I speed up a little? S speeds me up. Well, what's stronger then? If I speed up, what's stronger? Centrifugal is stronger, so I should pull away. Or doesn't it make sense if you're going around a corner and you speed up, you're going to take the corner wide, right? So I should actually like this, right? And I should go away. When I go away, what happens to my speed? I slow down. What's stronger now? Gravity pulls me in. I speed up. I get flung away, right? So elliptical orbits are that just oscillating back and forth, right? If I slow down, centrifugal force is stronger. And I speed up. I get flung out. I slow down, right? Back and forth like that. So let's try it here. I'm going to hit the S key. Hopefully it won't fling me off. One possibility is that I leave and I never come back. Oops. I have a feeling that'll come back though. Do you? It's back. It's back. Now here's something that some astute observer noticed. What's true about the old orbit and the new orbit? These are always, yes?
It goes from a perfect circle to
an ellipse, yeah. And what is true about the ellipse and the circle? They are tangent, yes. Yes, they are tangent, right? And we can use this to do orbits, right? So for example, okay, let's suppose we are in this orbit and we're way far from the moon and we want to set ourselves into an orbit, a circular orbit close to the moon. We have to fire the engines twice. Let's try it. Okay, here we go. 1, 2, 3, 4, 5. Okay, I'm just doing 5 times, right? Okay, now this is an elliptical orbit. How do I make it circular? Where do I fire it to make it circular? How do I bring this side in? Where do I fire it to bring that side in? The opposite side here. I'm going to slow down here, right? So I fired it once. Right now I wait until I'm in the right position. Got to wait a little bit here, waiting. Okay, are we ready for this? I'm going to fire it right here. There we go. That's kind of cool. It's not a perfect circle, but it's something, right? Isn't that cool? How do we get back to the old orbit? Speed up. Now I'm going to speed up. So let's see. Oops. I messed that one up, didn't I? Oops. I didn't listen to you. I should have listened to you. Okay, here we go. I'm going to go 3 times. There we go. Okay. And now I'm going to bring that other side in. So to bring the other side in, I do it on this side. There we go. So now we're orbiting. We pick up the lunar module. We want to move to a higher orbit or something. They didn't do this, but they could have. Okay. So now I need to speed up right where they overlap, right? Ooh, that's pretty good. Okay. And then if I wanted to, I could have boosted right there, but I'm going to wait around. So now I need to go to the old orbit, right? I'm going to go 1, 2, 3. There we go. Yeah, that wasn't as good, was it? There we go. But that's the idea, right? Okay, so when they do these things to move from orbit to orbit, that's what you can use. You can use the concept of tangent orbits like that, which is one of the things that's in the orbit lab that you need to do. Okay, that's kind of cool, isn't it? Okay, now your brain is still, and then we can do this. This is kind of fun, right? I can hit the R key and just move ourselves in. I'm just slowing down, right? Right. Well, as you move in close to what's happening to my speed? Whoa, baby! Ah! There you go. Okay. Okay, I read this book. It was like a popular science book, and they were trying to explain Newton's laws, and it was like this book from 1910 or something like that. But they should have known better even in 1910, right? Newton's laws were old stuff by then. But the guy said that a persistent force pushing the Earth toward the sun would eventually make it plummet into the sun. Is that true? No, a persistent force pushing toward the sun, if you could do that with giant thrusters or something, would make the Earth move incrementally closer to the sun, at which point it would speed up and be in equilibrium again, yes? So orbits are these sort of inherently stable things, right? Elliptical orbits are just ones where they oscillate in and out of being a perfect circle. Well, that's why things orbit black holes, right? It's actually, to get into a black hole, you got to head straight at it. If you head it all to the side, you're going to go around and around.